Okay, guys. Hope you had a good weekend. I'm going to try something new here. I've been working on this weekend. I was told that we can't come to the school to um, to make a video. I was going to come to the school and make a video on my document camera like I did last week, and then they said we couldn't come to the school, so I don't know if they're cleaning the school or they're just trying to make everybody stay away. I'm not sure. So I have this trial program, you can see it here, AirServer, that is recording what I have on the screen on my iPad, because I can't write on my computer screen, but I can write on my iPad screen. So what we're going to do today, and I'm hoping that this will work, I know this isn't as big as you would like it, but this is my iPad screen that you're seeing here, and so I'm going to be going through this stuff and working these problems on my iPad screen. Now, like this document, I can't write on it, so after we look at this question, then we'll go to a different program to actually work the question out. And I don't like having to do it that way, but hopefully we'll be able to do it. What we're going to do, if you will look at this test review, and I also have posted this on Google Classroom. This is our test review for Unit 4. I have 13 questions over the gas laws, and then you will see it starts over with number 1 again, and it goes to 10 again. Well, actually 13 questions. A few of those are multiple choice, and then we have one question over Boyle's, one over Charles, one Gay-Lussac, one combined, one ideal, one Dalton's law of partial pressure, and then a couple of mixed where you have to figure out which one it is and which equation to use. And then you have another over each one, just like before, and maybe a few more where you have to figure out which equation to use. So we're going to do the first 13 together right now in this video. And then the other 10 that I have on here, you are going to have to do on your own. And I am going to set the deadline for having those submitted to me by noon on Tuesday. Okay, so by noon on Tuesday, I need these other 10 problems worked out. And I will put an assignment on Google Classroom where you will, rather than putting it like a quiz or something, I'm just going to have you to work each problem, number them 1 through 10, and show me the work and your answer for each one. And then at noon, you should have those submitted, and I will send you the key to these 10 problems. I will work them out myself. I will take a picture of my work, and I will post it on Google Classroom. So you are going to, this is going to give you some time because the exam isn't till Wednesday. If you will look on Google Classroom, last night I posted our lesson plans, and our exam is on Wednesday. So today you're going to watch me work out some of these problems, and then from the time you watch the video until noon tomorrow, Tuesday, you will have to work the last 10 problems on this review sheet. Again, if you don't have a printer to print it out, that's fine. Just do it on some notebook paper, number them 1, 2, 3, 4, number them so I can tell, which one is which. Make sure you number it. Again, show me your work and circle the answer that you got. And then you will submit that by noon to me tomorrow, Tuesday. And then after noon tomorrow, I will upload the key so that you can look at what you got and compare that to the correct answer and see, and that will give you from noon tomorrow until Wednesday when you take the exam to study. So you go back and compare what you did and what you got to what I did and what I got. And if you have any questions, you email me, you make a comment on Google Classroom, and I will answer you. I will FaceTime you or Skype you or something if we need to, if you need extra help to work these out. But that way, that gives you a whole day to be able to work these out before you actually take your test. Your test will be on Wednesday. And Wednesday, I'll probably do similarly. I will post the exam, and then you will work the exam out just like you're going to work out this review. I will post the exam, and then you will have to submit it to me by Wednesday night. or I'm not sure it'll be by Wednesday. Yeah, probably by Wednesday night, because I want you to go ahead and get that exam out of the way before you start a new unit. And so um, therefore, and then anything that we do after Wednesday will not be due until Sunday evening. But I'm going to go ahead and require you to submit this review before the exam, and then to submit the exam before you start the next unit. And that exam will be due by Wednesday evening. I will post it Wednesday morning, and it will be due by Wednesday evening. And again, I'm just doing that because I want you to get finished with this unit before you start the next one. And I feel like that would be the best way to do it. I don't want to wait until I don't want you to be waiting till the last minute on Sunday evening to do an exam if you don't have to. So again, I'm giving you notice right now that you will have work due by about noon on Tuesday, and then you will have an exam due by 11:55 on Wednesday evening. And if you have any issues with that, then you need to let me know before this day is over, before Monday today is over. Okay. So let's go ahead and look at our multiple choice questions first on this Unit 4 review sheet. Again, the questions that you will have will be similar to I think I gave you some multiple choice questions last week to answer about the kinetic molecular theory. So you need to make sure that you understand all the parts of the kinetic molecular theory, and that's what these multiple choice questions will be about. So the first one, according to the kinetic molecular theory, particles of matter, and the answer to that one would be A, are in constant motion. The kinetic molecular theory, kinetic means motion, molecular is molecule, so molecules in motion. So particles of matter are in constant motion. Number 2, the kinetic molecular theory explains the behavior of. It explains the behavior of solids, liquids, and gases. If you remember, we talked about the motion and speed and space between solids, liquids, and gases. We took those notes, so the answer to that one would be letter D. It explains the behavior of solids, liquids, and gases. Number 3, an ideal gas is an imaginary gas. That is letter B, that conforms to all the assumptions of the kinetic molecular theory. Now remember, ideal gases are imaginary gases. They really do not exist. Ideal gases abide by all those assumptions of the kinetic molecular theory, but remember, real gases do not. Real gases, their collisions are not elastic. Real gases, there are attractive forces between the particles. Okay? Number 4, if two moving steel balls collide, their total energy after the collision is the same as before. This is an example of C, an elastic collision. Again, if the energy is exactly the same before and after the collision, that would be an elastic collision. Remember that generally all collisions are not elastic. And then number 5, by which process do gases take the shape of their container? That is letter B, expansion. Gases expand to take the shape of their container. So again, be sure that you are familiar with the different laws and what they say as far as Boyle's, Charles, and Gay-Lussac's. Be sure that you are familiar with the assumptions of the kinetic molecular theory. Be sure that you are familiar with how real gases do not obey the kinetic molecular theory. And be sure that you are familiar with things like expansion and compressibility and diffusion and effusion and things like that, because there could be questions about those things on your exam on Wednesday. So if you have any question about those things, make sure you let me know. Okay, moving on to our first problem, and I'm going to bring this up on my phone as well so that I can see it, because after we go through it on here, I won't be able to see it because I'll be going to a new program to be able to write, because I can't just write on this screen. I have to write on a different program. Okay, so the first question. Bacteria, and hopefully you have printed this out and have it in front of you while we're working the problem. If not, I really wish I could work it on the worksheet, but I don't have anything that I can record me working it on a worksheet on, so I'm having to improvise. Bacteria produce methane gas in sewage treatment plants. This gas is often captured or burned. If a bacterial culture produces 60 milliliters of methane gas at 700 millimeters of mercury, what volume would be produced at 760 millimeters of mercury? Okay, so what I'm going to do then is I'm going to go out of this. That is my Google Drive app, and I'm going to go into my paper app. This paper app will let me write on the screen. So I already have selected what I want to use, so now we're going to do this. So this is Boyle's Law, but again, remember that with Boyle's Law, we don't even have to use Boyle's Law. We can just use the combined gas law. So P1 B1 over T1 equals P2 B2 over T2. Okay? And then it says that we have 60 milliliters. And we have 700 milliliters of mercury. We have what volume would be produced, so that's a question, at 760 milliliters of mercury. Okay, so then obviously if it is it produces 60 milliliters at 700, so this is going to be milliliters as a volume, so that's going to be our V1, and millimeters of mercury is a pressure, so that's going to be our P1. And then we're looking for V2 if this is I'm sorry. Hold on just a minute, let me erase that. If this is P2. Okay? So, we'll notice we have P and V. We're saying nothing about T, so T must be constant. So, therefore, this is Boyle's Law. P1 V1 equals P2 V2. So, our P1 is 700. Our V1 is 60. And our P2 is 760. And our V2 is what we don't know. All right? So now we're going to erase some of this up here so that we can solve. I'm sorry, this is going to take me a while. All right? So, obviously, I hope you can see here, we're going to have to divide both sides by 760. All right? So we're going to have 700. I can't touch the screen. And I'm just going to say millimeters Hg times 60 milliliters equals, okay, and then we said we were going to have to divide both sides by 760. And that is going to be equal to V2. So again, when we divide both sides by 760, 760 is gone on this side, and then we have 760 under these on the other side. And I'm sorry. So now I've got to push this in my calculator, and I'm going to do 700 times 60 equals, divided by 760 equals, and then I get 55.2631579. Our millimeters of mercury cancel out so that our unit will be milliliters, and we're going to have V2 is equal to, and then it looks like we're going to need 3 significant digits because that's the least number, so 55.26 rounds to 55.3, so 55.3 milliliters is going to be our V2, okay? And let me know if you have any questions about that. And I wonder if there's a way that I can just like get rid of all this at the same time instead of me. Let me just X out. Oh, why not? Yeah, let me X out of that. Okay. No. If there's a way I can do that. Yeah, let me leave it like that. And then we'll go on to the next one. Okay. So, let's go back to our problem. Let me figure out how I want to do this. All right, let's go back to another problem. Number 2. or the second one I should say, Charles' law. A helium-filled balloon has a volume of 275 or 2.75 liters. At 20 degrees Celsius, the volume of the balloon increases to 2.46 liters after it is placed outside on a cold day. What is the outside temperature in degrees Celsius? Okay. So, again, we're not even going to worry about that this is Charles's law. We're just going to go back and use again our combined gas law equation. That's the easiest way to do it if you ask me. So, and let me turn on my pen here. So P1, B1 over T1 is P2, T2 over B. Oh, I'm sorry. I don't know what I'm thinking here. It should be PB over T, and I'm doing the wrong thing. You can tell I'm a little bit perturbed here trying to figure this out. So B2 over T2. Okay, so it says that we have 2.75 liters. We have 20 degrees Celsius. We have 2.46 liters. And we have, what is the temperature? Okay, so you can see liters is going to be a volume. And then Celsius is going to be a temperature, so we don't need pressure here. Okay, so then we have V1 T1, V1 over T1 equals V2 over T2. So another thing you see here, we're going to have to change the Celsius to Kelvin. So we're going to add 273, which is going to give us 293 Kelvin. And then the volume is 2.75 liters at 20 degrees. So this is going to be V1 and T1. So this is going to be V2, and we're solving for T2. So let's plug it in. V1 is 2.75 liters. T1 is 293K. V2 is 2.46 liters. And T2 is what we don't know. So what we want to do here then is we'll cross multiply, and we'll have 2.75 liters times T2 equals 2.46 liters times 293K. And then to solve for T2, we'll divide both sides by 2.75 liters. These will cancel out. Liters will cancel out. And we're going to have T2 is equal to something here. So now we're going to punch that into our calculator, and we're going to have 2.46 times 293 equals. And then we're going to divide by 2.75 equals. And I get 262.101818. Well, as you can see here, 3 significant digits is my least number, so I need 3, so 262. And that is 262K. Now, if that asked us for Celsius, we would subtract 273. But I don't think the problem asked us for Celsius. Let's look and make sure, but I don't think it did. No, it just said, no, it does say, what is the outside temperature in degrees Celsius? So then we're going to have to go back here, and we're going to have to subtract 273. So minus 273 equals. And notice this is going to be a negative number. 262 minus 273 is negative 11. So negative, and what I'm actually going to do here, I think, guys, since this is, I'm not done, since this is not my final answer, I'm going to go ahead and not round that yet, because I forgot that it was asking us for degrees Celsius. So let's not round it until we get to our final answer. So again, 2.46 times 293 equals, divided by 2.75, and I get 2, sorry, I gotta go back to my pen, 262.101818. So minus 273 from that, minus 273, and that gives me 10.891818. And if I need three significant digits, 10.89 rounds to 10.9, and it's negative 10.9 degrees Celsius. And don't forget to put your unit on there. Okay? Let's go to our next question then. Moving on. Gay-Lussac's law. Prior to a trip, the pressure in a truck tire was 1.80 atmospheres when the temperature was 20 degrees Celsius. When the trip was over, the pressure was 1.90 atmospheres. Assuming constant volume, what was the temperature? Okay, so let's go back to our page. And this is one where I'm going to have to erase, I think. Clear all. There we go. I knew there was an easier way to do that. I just couldn't remember it. Okay, so again, I'm going to go ahead and use that combined gas law. P1, V1 over T1 equals P2, V2 over T2. And let's see what it gives me. It tells me that there was 1.80 atmospheres. There's 20 degrees Celsius. There's 1.90 atmospheres. And there is what was the temperature. So we know we're looking for a T. So we know atmospheres is a P. And we know Celsius is a T. Okay, so this means, and it did tell us in the problem, assuming constant volume. So we're going to delete the volume, and we have P over T, which we assume that is Gay-Lussac's law. Now, it says the pressure in the truck tire was 1.80 atmospheres when the temperature was 20. So we're going to say this is P1 and T1, this is P2, and we're solving for T2. So P1, then we're going to substitute these numbers in. 1.80 atmospheres over, oh, wait a minute. Before we do that, we've got to change this 20 degrees to Kelvin. So we've got to add 273, and that gives us 293 K. And so that's 293 K. That is a 2. And then P2 is 1.90. And T2 is what we don't know. So we're going to cross multiply, and we're going to get 1.80 atmospheres times T2 is equal to 293 K times 1.90. And that is atmospheres. We don't want to forget that. So to solve for T2, we're going to have to divide both sides by 1.80 atmospheres. And that cancels that out on that side. Atmospheres cancel out over here. And we have T2 is going to be equal to, let me get my calculator back up in here. It's going to be equal to 293 times 1.90 equals divided by 1.80. And we get 309.277778, and that will be K. And then before we get our final answer, let's look at what it asked us as far as, it says, what is the temperature in degrees Celsius? Or no, this one doesn't. The last one said in degrees Celsius, but this one doesn't. This one just says, assuming constant volume, what was the temperature? So we can leave it in Kelvin, then we don't have to change it back to Celsius. So if we look, everything has 3 significant digits, so 3 significant digits here, 309.277778 rounds to 309K, and we'll just leave it at that. And we'll not worry about taking it to Celsius because it didn't tell us we had to. If it was like the one before it and it said in degrees Celsius, we would have to subtract 273. But since it didn't, we won't. All right. So going back to our problem. Our problems again. Combined gas law. An unopened cold 2-liter soda bottle contains 46.0 milliliters of gas confined at a pressure of 1.30 atmospheres at a temperature of 5 degrees Celsius. If the bottle is dropped into a lake and sinks to a depth at which the pressure is 2.85 atmospheres and the temperature is 2.09 degrees Celsius, what will the volume of the gas in the bottle be? Okay, so let's go back to our paper. And I don't know why it's like that, because I don't want it to be like that. Let's go ahead and go back to this one, and let's clear all. All right. Now, so again, our combined gas law. This makes me mad. Sorry, guys. I know it's taking up a little bit longer than what we would like, but all right. Let me move over to the center a little bit. So my combined gas law, P1 V1 over T1 equals P2 V2 over T2. All right, so let's look at this problem. An unopened cold 2-liter soda bottle, so 2.00 liters. That's a 2. 46.0 milliliters. 46.0 milliliters. 1.30 atmospheres. 5.00 degrees Celsius. It's dropped into a lake. The pressure is 2.85 atmospheres. Temperature is 2.09 degrees Celsius. What will the volume of the gas be? Okay. So, now I want you to notice something here. It says an unopened cold 2-liter soda bottle contains 46 milliliters of gas. Okay. So, do we need that 2.00 liters? No, we don't. That is just some extraneous information they've given us that just to kind of throw us off a little bit. We don't need that. It contains 46 milliliters of gas, so we know that is a volume of gas at a pressure of 1.30 atmospheres, so that's a pressure. At a temperature of 5, so we know that's a temperature. It's dropped into a lake and sinks to a depth at where the pressure is 2.85 atmospheres, so that is another pressure. The temperature is 2.09, that is another temperature, and we want to know what the volume would be. So, if it has this volume, this pressure, this temperature, and then we drop it into the lake, and this is the new pressure, the new temperature, and we want to know what the new volume would be. So, we have to use all three of these here because we are given all three. We got to solve for all. We got to do all three here. So again, before we do anything, let's go ahead and convert our Celsius to Kelvin before we forget. So plus 273, that's going to give us 278 K. And then if we do 273 here, that's going to give us 275.09 K. Okay. So then we're going to substitute in our numbers. 1.30 atmospheres. V1 is 46.0 milliliters. And T1 is 278K. And then P2 is 2.85 atmospheres. T2 is 275.09 K, and then V2 is what we're solving for. So what I'm going to do here is I'm going to, you can do this different ways. I think I'm going to go ahead and kind of multiply and divide everything out before I start solving for my V2. So I'm going to go ahead and do my left side. And I'm going to do 1.30 times 46.0 equals divided by 278. And I'm going to get an answer there, 0.21510791. And then on the other side, I'm going to have 2.85 times 275.09, and that is 784.0065, and that's over V2. So now I can solve for V2 by simply switching places with those two, and I'm going to go ahead and go back up here so that I don't run out of room down here on the bottom. Basically, you can see what we're going to have to do is we're going to have to multiply both sides by V2 and then divide by 0.2151071. And so we're going to end up with V2 is equal to 784.0065 divided by 0.2151071. Okay? So 784.0065 divided by 0.2151071 equals, and I get 3644.71255. Now, before we go any further, let's go back and look here and see. Notice that our volume has went up from 46 milliliters to over 3,600 milliliters, which is over 3 liters. So let's make sure that that sounds like that would be correct, okay? Just based upon what we're seeing here. We are seeing here that the temperature is going down and the pressure is going up. So I really don't think that the volume should be going up, because when temperature goes down, volume should go down. When pressure goes up, the volume should go down. So I've not done something correctly here. Let's go back and look again. P1V1 over T1 equals P2V2. Oh, I see what I did wrong. And you guys probably noticed it already, but temperature should be on the bottom here. So of course I messed up. But see how I figured out how I messed up? And you guys knew long before me, and you weren't here to tell me that I messed up. So therefore I had to go through all that and figure out that I messed up. But that's part of it. All I did was mess up on this side though. So it's okay. It's okay. I knew that 3,600 didn't really sound correct. And I hate that I put you all through all that. Wish you had been here to tell me I was doing it wrong. Okay, so now let's try this again. So P1V or P2V2 goes on the top over T2, which is 275.09. Okay? And so that means this is wrong as well. I'll get it right here in a minute. If you guys want to, if you want to go ahead and forward through me erasing, you can. Okay, let's try this again. All right, so over here, 1.30 times 46.0 equals divided by 278. Oh yeah, that wasn't wrong. 0.2151071. On this side, that's what's different. 2.85 divided by 275.09. Okay, 0.01036.025 V2. Now we're going to have to divide both sides. So V2 is going to be equal to 0.2151071 divided by 0.01036.025. All right, so now 0.2151071 divided by 0.01036.025 equals, and I've got 20.762810.7, and obviously this was K, so our K's are canceling out. And our atmospheres are canceling out. And what we have left is milliliters. Now, look at this. It looks like we need 3 significant digits. So 20.76 rounds to 20.8 milliliters as a final answer. And so as we can see here, our volume went from 46 milliliters to 20.8 milliliters. And when we go back and look at our problem, that makes sense. The temperature went down, which means volume should go down. As it gets colder, the volume decreases. Remember, we talked about the helium balloons on Valentine's Day. Also, as the pressure goes up, the temperature decreases. The volume decreases. Again, more pressure is pushing those particles in closer together, causing the volume to decrease. So yes, definitely the decrease in volume from 46 milliliters to 20.8 milliliters sounds correct. Okay. Moving on to the next problem. We have the ideal gas law. A camping stove uses a 5.00 liter propane tank that holds 3.00 kilograms of liquid C3H8. And again, you guys, that 3 and that 8 should be subscripts, okay? So 3 carbons, 8 hydrogens. How large a container would be needed to hold the same amount of propane as a gas at 25 degrees Celsius and a pressure of 3 atmospheres? Okay, so we know we're going to be using the ideal gas law. The ideal gas law, remember, is PVNRT, or PV equals nRT. So let's go back over here and go to another one, and let's clear everything, clear all, and then go back to my pen. So again, PVNRT, PV equals nRT. All right, and we are given a 5-liter propane tank, so 5 liters. We are given 3 kilograms of C3H8, so 3.00 kilograms. And we are given 25.0 degrees Celsius. And we are given a pressure of 3 atmospheres. Okay, so we know that liters is a volume. We know that atmospheres is a pressure, and we know that 25 degrees Celsius is a temperature, and we also know we're going to have to convert that to Kelvin, so 273. So 25 plus 273 is 298 K. Now, we also need an N. Remember that R is our constant, and since we're using atmospheres here, then that means, and I don't know if you guys can remember this or not, but I have to look it up. The R, when you're using atmospheres, remember if you're using kilopascals, it's 8.31. But if we're using atmospheres, it's 0.0821. So R is going to be 0.0821 liter atmosphere over mole Kelvin. Okay? So again, sorry I had to look that up. Going back to our problem now. Sorry about that. All right. So we know N is a number of moles. Well, kilograms is not moles, but we could use kilograms of C3H8 to get moles. Okay? So what I'm going to do is I'm going to do this is hard for me to write. 3.00 kilograms over 1. And then I know I want to go from kilograms to grams. And I know that there are 1,000 grams in 1 kilogram. Now that I know now that I've got it to grams, kilograms cancels out, then I can change from grams to moles by using the periodic table. So again, carbon, there's 3 carbons, so that's 36. And there's 8 hydrogens, and so that's 8. And so 44 grams in 1 mole. So 44.0 grams in 1 mole. So then, got to use my calculator. And let's do 3 times 1,000, which is 3,000, divided by 44. And that gives me 68.181818. Basically, it's repeating, and that's moles. So, 3 kilograms of C3H8 is 68.181882 moles, which is my N. Okay, so now we got to do a substitute in. And we're solving for, what did it ask us we were solving for? Let me go back and look at it again. Sorry. Okay, I am solving for, it says how large a container would be needed to hold the same amount of propane at da-da. So again, this one kind of gives us a, it tells us that we're holding it in a 5-liter tank, okay? But it says how large of a container would be needed if we have a temperature of 25 and a pressure of 3 atmospheres. So right now we have it in a 5-liter tank, but what we're saying is we're going to change the temperature and the pressure. How will that change the size of the tank? So this is not this is not the volume that the volume is what we're looking for, because it says how large of a container. So we're looking for the volume of the container that we would need, because we have it in a 5-liter tank right now, but we're going to change the temperature and pressure, and let's see how big of a volume we would need for the new container. So PV equals nRT. P here, we're going to have a pressure of 3 atmospheres. The V we don't know. The N we said was 68.18182 moles. The R is 0.0821 liter atmosphere mole Kelvin, and I'm going to leave that off because I don't have enough room for it. And then the T is 298 K. Okay. So to solve for this, we're going to have to divide both sides by 3 atmospheres. Okay, this will cancel out over here. And then that atmosphere would cancel out with the atmosphere in the R here. Okay, and so V is going to be what we get. And then, of course, our mole will cancel out in our R, our K will cancel out in our R, and what we're going to be left with is liters in our R. Okay, so now we're just going to have to substitute this into our calculator and see what we can get here. Okay, so we've got 68.18182 times 0.0821 times 298 equals, and then divided by 3.00, and that is an O there, guys, by the way. I know it's hard to tell. Divided by 3.00. And that gives us 556.040909, and again, that is liter. And so now let's look at our significant digits. It looks like all of these have 3 significant digits. So to 3 significant digits, that's going to be 556 liters. Okay, so what this is saying is obviously this propane in a 5-liter tank, if we change the temperature so that we have 25 degrees Celsius and our pressure is 3 atmospheres, the volume of that gas is going to increase. And so that is the reason why we have to, we're going to have to put it into a bigger container here, obviously. A lot bigger container than 5 liters. It looks like the volume increased 100 times. Now, again, I don't have the answer sitting here in front of me. I'm assuming I substituted everything incorrectly. 3 atmospheres, volume, 68 moles, because 3 kilograms is 3,000 grams, which is like 68 moles. The 0.0821 for atmospheres, and the temperature is 298 K. 25 degrees Celsius is 298 K. So then to solve for the volume, the new size tank, Actually, we're probably going to have to put it in a tank a little bit bigger than that because um, we got a little bit more than 556, so you might even have to say like a 557 liter container. Just make it a little bit bigger container because we have a little bit more than 556 liters here. We have 556.04 liters. Okay? So, looking at the next problem, Dalton's law of partial pressure. The total pressure inside of a container holding 25.5 grams of nitrogen gas collected over water is 50 kilopascals. If the temperature is 63.5 degrees and the volume is 552 milliliters, what is the partial pressure of the water vapor? Okay, so the first thing we got to do is find the pressure of the water vapor, because we really don't know what the proportion is. The temperature is 63.5 degrees Celsius and the volume of the gas is 552 milliliters. What is the partial pressure of the water? So what we've got to do here, you see the total pressure inside of a container holding 25.5 grams of nitrogen gas collected over water is 50 kilopascals. Okay, what we're going to have to do here first is we're going to have to convert 25.5 grams of nitrogen to moles, and then figure out what part of that pressure is nitrogen. Or no, let me see here. Partial pressure of the water vapor. The temperature is 63.5 degrees. The volume is 552 milliliters. What is the partial pressure of the water vapor? So 552 milliliters is the volume. 63.5 degrees is the temperature. The total pressure is 50 kilopascals. We can figure out the partial pressure of the nitrogen. No, we can't, because we don't know the pressure of the water vapor yet. Okay, so to get the pressure of the water vapor, we know the temperature, we know the volume, we need a number of moles, but we don't have that. Maybe something is missing here. I guess we can change the nitrogen to moles and figure out the part. Yeah, that's what we can do. We can change the nitrogen to moles and figure out the number of moles of nitrogen, and then get the partial pressure of the nitrogen, and then subtract that from the total pressure to get the pressure of the oxygen. That's what we have to do. Okay. So sometimes you just have to think about this for a minute. So let me open this up so I'll have it here in front of me. All right. So let's go to our paper. Go out of this one. We'll go to this one. And we will clear off. Now, so we're going to have to actually do a couple of different things here. The first thing we're going to have to do is figure out the partial pressure of the nitrogen before we can figure out the partial pressure of the water. So we're going to be using PV equals nRT first. Okay, and we know, and we're going to be solving for the pressure. The pressure of the nitrogen is what we're looking for. And so I'm putting pressure of nitrogen here. Okay, that's my question mark. And so V is 552 milliliters. N is what we got to find. We know that there are 25.5 grams of nitrogen, so we'll look at that in just a minute. Our R, let's go ahead. Okay, it gives us the total pressure of 50 kilopascals, so we're going to use the kPa R here. And so let me find the kPa. Sorry, let me see here. The kPa is 8.31 liter kPa, mole Kelvin. Okay, so 8.31 liter kPa over mole Kelvin. And I'm sorry, but I'm having trouble writing. Okay. I have to keep opening up the problem again. Okay. And then, so we did R, and then T is 63.5 degrees Celsius. We know we're going to have to add 273 to that. And then our grams was 25.5 grams of nitrogen, which we're going to have to convert to moles. And remember, nitrogen gas is diatomic. It's part of Brinkelhoff. So 1 nitrogen is 14, so 2 nitrogens is 28. So we got a couple things we need to do here. We need to change grams of nitrogen to moles of nitrogen to get our N. And then we have to change temperature to Kelvin. So let me put this in my calculator. 63.5 plus 273 is 336.5. And then 25.5 grams divided by 28 is 0.9107142 moles. So that's what we'll put up here for N. 0.91071429 moles. Okay. So now we can substitute everything in. Again, what we had to do here, we are looking for the pressure of nitrogen. Once we know the pressure of nitrogen, we can just subtract that from that total pressure of 50 kPa's to find the pressure of oxygen. So, pressure times the volume, which is 552. And you guys, another thing here that is a problem is we have, this is liter kPa's. Okay, it's liters. And I have milliliters. So we have to change that to liters. There's 1,000 milliliters in 1 liter. So that means we have to divide by 1,000 or move your decimal 3 places to the left. So that's 0.552 liters. So 0.552 liters. So P is what we're solving for, times 0.552 liters is equal to our N, which is 0.9107142 moles. Our R is 8.31, and I'm not going to put all those units right here because I don't have room. And then our T is 336.5 Kelvin. Okay, so to solve for this, we're going to have to divide both sides by 0.552 liters. Liters are, this is all going to cancel out on this side. Over here, liter will cancel out with the liter in the R. Mole will cancel out with the mole in the R. And K will cancel out with the K in the R. And so we're going to have P is equal to, and then we're going to take that 0.9107142 times 8.31 equals, divided by 0.552 equals, and that is 13.7102096. And notice the only unit not canceled out in our R is the kPa, so that is kPa's. Now again, that is the pressure of the nitrogen. And we want to know, the question asks us for the pressure of the water vapor. Well, remember, according to Dalton's law of partial pressure, and let me go ahead and erase this real quick up here. so that we can put this in. Okay. Remember that the total pressure is going to be equal to the pressure of the part. So the pressure of the nitrogen plus the pressure of the water. All right, so this was pressure of nitrogen is what we found here. So the problem told us that the total pressure was 50 kPas. I think that was right. Let me look and see before I say that for sure. I do not like having to switch back and forth here, guys, but I'm doing the best I can do, so you'll just have to bear with me. Yes, it was 50.0 kPas. So that should be a 0.0 there. Minus, let's say 13.7 here. Or equals 13.7 kPas plus H2O. So obviously, what we're going to have to do here is we are going to have to subtract. We're going to have to subtract the 13.7 from both sides. And again, I'm just making a little bit more room because this iPad screen is kind of small. I need a bigger iPad. But guys, I can't afford to buy one right now, so you just have to bear with me. So what we're going to have to do then to solve for the pressure of the water is we're going to have to subtract 50 minus 13.7. And I think that's 36.3, but I'm going to type it in my calculator just to make sure because it's kind of late at night right now and my brain is fried. 13.7. Yes, 36.3. So 36.3 kPas would be the partial pressure of the water. So in that problem, you had to use the PV equals nRT to find the pressure of the nitrogen. And then once you find that, you have to subtract that from the total pressure, which they gave you in the problem was 50.0, to get the pressure of the water vapor. All right. So now we have a couple of mixed gas law problems that we're going to do. And I'm going to go ahead and clear these out before I do that, just because I know we're going to need at least 2 of the 3 of them. Okay. Now let's go back to our problems. We are on the mixed gas laws. A radioactive metal atom decays by emitting an alpha particle, which is a helium nucleus. The alpha particles are collected as helium gas. A sample of helium with a volume of 12.05 milliliters was obtained at 765 millimeters of mercury and 23 degrees Celsius. How many atoms decayed during the period of the experiment? Okay, so let's go back to our paper thing here. And let's see what we're given so we can decide, because this is one where it didn't tell us what kind of gas law we're using. We have got to figure that out for ourselves, because this is a mixed gas law problem. Okay, so it gives us a volume of 12.05 milliliters. Volume of 12.05 milliliters. It gives us a pressure of 765 millimeters of mercury, and it gives us a temperature of 23.0 degrees Celsius. And it wants to know how many atoms decayed during the period of the experiment. Well, you guys, atoms, what can I relate atoms to? There's only one thing that we talked about that we can relate atoms to, and that's moles. So in order to figure out the number of atoms, we're going to have to do the number of moles first. So we're going to be looking for N, which is the number of moles. And so guess what we're going to have to do? PV equals nRT. Okay? So now we know we're going to have our temperature in degrees Celsius. So we're going to go ahead and add 273, and that's going to give us 298. Also, we know that our R is either going to have to be in kilopascals or in atmospheres. I choose to do atmospheres because I'm more familiar with those. And so that means I'm going to have to change my millimeters of mercury to atmospheres. So remember that 760 millimeters of mercury is equal to 1 atmosphere. So let's go ahead and change that. 765 millimeters of mercury. We're going to change that to atmospheres. Millimeters of mercury to atmospheres. Again, 1 atmosphere is 760 millimeters of mercury. So what we're going to do here is we're going to do 765. It's going to be really close to 1, guys. 765 divided by 760. That gives us 1, so we're going to do this in atmospheres, 1.0065789 atmospheres, okay? And then I know that this is going to need to be liters, so 12.05 milliliters, and I know I need to change that to liters, 1,000 milliliters in 1 liter. Or just move your decimal 3 places to the left and you get 0.01205 liters. Okay? So, and I'm going to check that just to make sure. Yeah. 0.01205 liters. Okay? So now I'm going to clear off. I'm just going to have to erase all this conversion that I did. So now that I have, remember that our rest of the units in our problem have to match our R. So therefore, I had to convert my millimeters of mercury to atmospheres, and I had to convert my milliliters to liters because your units have to match your R. And again, I told you that we want to use the R here that has atmospheres in it because I'm just more familiar with atmospheres myself. And so our R that we're going to use is 0.0821 liter atmosphere over mole Kelvin. Okay? So now we can plug in everything. Every time I write too close to the edge, it does that. Okay, so P is 1.0065789 atmospheres. V is 0.01205 liters. N is what we're solving for. 0.0821 is our R, and then 298 is our temperature. Okay, so to solve for N, we're going to have to divide both sides by 0.0821 times 298. Okay, and so those will be gone, and this will be equal to N. Now, our atmospheres will cancel out with our atmospheres and our R. Our liters will cancel out with our liters and our R. Our K will cancel out with our K's and our R. And what we'll be left with is moles, which is what we're looking for here. So we're going to do 1.00657895 times 0.01205 on the top. And that gives me 0. And again, I'm not rounding till the very end. 1212928 on the top. On the bottom, 0.0821 times 298 gives me 24.4658. Okay. And so 0.0121298 divided by 24.4658 is equal to 0.0004956 moles. Now again, we're not done here because it asks us how many atoms decayed. So now that we have moles, we've got to change moles to atoms. Okay? And I hope you remember how to do that. So 0.004956 moles over 1. We're going to change moles to atoms. And remember that 1 mole is 6.02 times 10 to the 23rd atoms. Okay? So you have to take that number and multiply it. So, and again, this is where you're going to, if you don't have a scientific calculator at home, you're going to take your iPhone calculator, turn it landscape, turn it horizontal, and it will turn into a graphic or to a scientific calculator. So 0.00049576 times 6.02 23 equals. And then again, if we look at all of our numbers, we need 3 significant digits. So again, I've got 2.9844752. I need 3 significant digits. So 2.984 rounds to 2.98. And then guys, don't forget you have an exponent over there. It says E20. So that means times 10 to the 20. 10 to the 20 atoms. And this is not our N. So I'm going to erase that. This is actually our atoms. Okay, so our N was this. This was our N right here. But that's not what it asked me for. My final answer would be right here. Number of atoms. I took my 0.00049576, changed it to atoms by multiplying by 6.02 times 10 to the 23rd, and I got 2.98 times 10 to the 20 atoms. Okay? One more problem to do, and then you're going to get to do some on your own. And that is this last one here. A 12.5 gram sample of oxygen gas is added to a 25 gram sample of nitrogen gas in a 25 liter container at 28 degrees Celsius. Calculate the partial pressure of each gas and the total pressure of the mixture. Okay, so obviously when we see grams there, I hope you're thinking, oh, moles. I need moles. And then once we have moles, and once we have, and we also have liters, which is volume, and Celsius, which is temperature, we can solve for the pressure of each gas. And then once we get the pressure of each gas, we can add them together to get the total pressure of the mixture. So let's go ahead and write down what we were given on our page. Okay, so we have a 12.5 gram sample of oxygen gas. So 12.5 grams of O2. We know we're going to have to convert that to moles, guys. How do I know this? Because none of our equations uses grams, but we do have one that uses moles. And so if I'm given grams, I know I'm going to have to convert it to moles. So oxygen is part of Brinkelhoff. It's O2. 1 oxygen is 16, so 2 oxygens is 32. So let's convert that to moles first. And 12.5. I cannot punch this in the calculator, guys. I don't know what's wrong with me. 12.5 divided by 32 gives me 0.39065. And I can't get the 5 on there. 5 moles of oxygen. Now let's do the same thing for the other gas that we were given, which I don't remember what it was, and I have to go back to the problem to see. Okay, it was 25 grams of nitrogen, so 25.0 grams of nitrogen. And again, nitrogen is also part of Brinkelhoff, so that is 1 nitrogen is 14, so 2 is 28. So we got to do 25, and that gives me 0.89285,714, and that is moles of nitrogen. Okay? So, and again, I've got to go back to the problem because Google will not keep my document open. All right. We also have a 25 liter container, so You know that is a volume, 25.0 liters. 28 degrees Celsius, 28.0 degrees Celsius. We know we're going to have to convert that to Kelvin. So 28 plus 273 is 301. And obviously here we're going to be using PV equals nRT. Again, I just like the atmospheres better, so we know then that we're going to use 0.0821 liter atmosphere mole Kelvin as our R. Okay, so let's start substituting in. I'm going to write my equation up here at the top. Pivnert. Okay, so my pressure is what I'm looking for, and let's go ahead and do oxygen first. Volume is 25 liters. N for our oxygen is 0.390625 moles. R is our 0.0821. And then our T is 301. We know we're going to have to divide both sides by 25 liters. So we know that the pressure of oxygen is going to be all this when we multiply it and divide it. So again, my liters in my R will cancel out. My K in my R will cancel out. My moles in my R will cancel out. And what I will be left with will be atmospheres. So we're going to punch this in our calculator. Our 0.390625 moles of oxygen times our 0.0821 for R times our 301 for temperature equals divided by 25.0. And I'm going to go ahead and round this to my correct number of significant digits, which again it looks like we're going to need 3. So 0.3861 is going to round to 0.386. And I'm going to substitute this in one more time in my calculator just to make sure I did it right. And you guys, if I were you, especially on the exam, I would do this more than once. 0.390625 times 0.0821 times 301 equals divided by 25 equals. And I got the same thing again. All right, so now I'm going to make me some room up here to do my next one by erasing this because I don't need the moles of oxygen anymore. I just use them to find the partial pressure of oxygen. Oh, shoot. And now we're going to have to do the same thing to find the partial pressure of the nitrogen. So again, I know I'm doing PV equals nRT, so now I'm doing pressure of nitrogen times the same volume, which is 25 liters, is equal to, okay, we have a different number of moles here, so it's 0.89285,714 moles. That's a 4. Our R is the same, 0.0821. And then our T is the same, 301K. And then again, we're going to do the same thing. We're going to divide both sides by 25.0 liters. Again, 25.0 liters on this side is going to cancel out. Here, the liters is going to cancel with the liters in R. The K is going to cancel with the K in the R. The moles is going to cancel with the moles in the R. And we're going to have the pressure of N2. And then I've got to substitute these numbers into my calculator. So 0.89285,714 times 0.0821 times 301 equals, divided by 25 equals. And I got 0.882575, and again I know I need 3 significant digits, so 0.8825 rounds to 0.883, and that is, again, these are atmospheres for both of these. Again, now I need to make just a little bit more room here to finish the problem up. Now that I know the partial pressure of oxygen and I know the partial pressure of nitrogen, then I can calculate the total pressure by using Dalton's law of partial pressure. The total pressure is equal to the partial pressure of the oxygen plus the partial pressure of the nitrogen. So the partial pressure of oxygen is 0.386. The partial pressure of the nitrogen is 0.883. And so the total pressure is going to be 0.386 plus 0.883. And again, I'm going to do, since I'm adding here, I do the least number of places past the decimal, which is 3. So 1.269 atmospheres. So our answers are pressure of oxygen is 0.386 atmospheres, pressure of nitrogen is 0.883 atmospheres, total pressure is 1.629 atmospheres. Okay, so I know that was a lot of work, guys. Believe you me, I understand because I just sit here and did it. So anyway, now it's your turn. The last part of this review, so that's going to be the number 1 starting here, all the way through the number 10. I want you to do for me for tomorrow. So I need you to have this done for me for tomorrow by noon. If you don't have it submitted to me by tomorrow at noon, you will not be able to submit it. Because once I have posted the answers, then I'm not taking your work anymore because I gave you the work. And all you have to do is copy it. And I'm not, no. So you must submit the answers to these 10 problems. And I don't just mean the answers. I mean the work. I'm going to put a document on Google Classroom, an assignment where you can do one of 2 things. I will put a document on there where you can actually take pictures of your work and insert the photo and submit it. Or if you can't figure out how to insert the photo, if you just want to take pictures of your work and submit the pictures, that's what you're going to have to do for me. And then about 12:30 tomorrow, I will post the answers. I will work these other 10 problems and I will post the answers. I will post pictures of the answers on Google Classroom. Again, if you have not submitted this to me by 12 tomorrow, noon, you won't be able to submit it at all. And then remember that I will be posting your exam tomorrow morning, so you better be studying. Tomorrow night, Tuesday night. Comparing your answers that you got to the answers that I put online to see where you made mistakes, if you made any. And then your exam will post at about 8:30 tomorrow morning, and it will be due by 11:55 tomorrow evening. Again, we're going to go ahead and do that exam on Wednesday and be done with it. So that, and then the rest of the things that I post for you to do for the rest of the week will be due by Sunday. But the exam, your review questions are due tomorrow at noon, and your exam will be due Wednesday night at 10:55. Please let me know if you have any questions or concerns. I don't care if you need me to Skype with you or anything like that. I will be glad to do that for you. Hope you have a good rest of your day. Talk to you later. Bye-bye.